143. Finite mathematics. In the previous sections, we learned how to describe sets, perform set operations, and count the number of elements in unions and intersections. Today, we are going to study a new counting technique called the multiplication principle. So, the multiplication principle is useful when a process is completed in several steps. For an example, think about choosing an appetizer and entry. When we go to the restaurant, we have the menu card and we wanted to select an appetizer and one entry. But there are a lot of appetizers and entries that we can select. Also, that means the process is completed in several steps. We can select one appetizer and the one entry, then the second appetizer and first entry. Also, the second example, creating a password. It says 8 characteristics, one numerical character and one special character and capital letter. There are a lot of ways that we can process that password. Also, choosing a route between towns. Think about we have 3 towns A, B, Z. There are 2 ways to go for a town A to town B, and there are 3 ways to go for a town C from B to C. That means we can select different routes to go from A to town C. Also, the main thing, think about when you select the courses per semester. So you have different combinations, you have different courses. So instead of listing every possible outcome, the multiplication principle allows us to count them quickly. So therefore, by the end of today's lecture, you should be able to recognize when the multiplication principle applies, use the multiplication principle for 2-step processes, use the generalized multiplication principle for several steps, verify answers using list or tree diagrams, and solve counting problems involving menus, passwords, license plates, schedules, and experiments. Okay, let's see why we need a new counting method. Some counting problems are simple enough that we can list every possible outcome. But listing becomes difficult when the number of possibilities grows. Suppose a restaurant offers, for example, suppose a restaurant offers 3 appetizers, 2 soups options, and 10 entries. So we could try to list every possible meal, but that would take time, right? So we could try to list every possible meal, but that would take time. So instead, we can use the multiplication principle. So the key idea is that a complete outcome is built by making one choice at each stage. Not that. The key idea is that a complete outcome is built by making one choice at each stage. Okay, then let's see what is the multiplication principle means. The multiplication principle. Suppose a process consists of two tasks. Suppose a process consists of two tasks. If the first task can perform in m ways, if the first task can be performed in m number of ways, and the second task can be performed in n ways, then the complete two-step process can be performed in m times n ways. Let's see the example. So, from town A to town B, there are two routes, route 1, route 2, right? From town B to town C, there are three possible routes, 3, 4, 5. Then the first task that we can complete we can go from town A to town B two ways, right? And we can go from town B to town C three ways. In total, we can perform this task. That means we can go from town A to town C, 2 times 3 ways, 6 ways, 6 different routes. Let's see. So from A to B, when we select from A to B, route 1, we have 3 choices to go for a B to C. 1, 3, 1, 4 or 1, 5. If we select A to B, route 2, again we have 3 possibilities, 3 possible routes from B to C. There are 6 different ways that we can go from town A to town Z, 1, 2, 3, 4, 5, 6. So we can complete this two-step process with m times n ways. So we multiply because every possible choice from the first task can be paired with every possible choice from the second task. Right? Okay. One more simple example. Suppose you have 3 shirts and 2 pairs of pants. How many different outfits can be made? How many different outfits can be made? So each shirt can be matched with each pair of pants, right? We have shirts, three choices, right? So let's use like this. 1, 2, and 3, right? Also, we have 2 pairs of pants. One and 2, right? So in first, we can match the first shirt with either pair of pants. 1, 2. We can match the second shirt with either one, and we can match the third one with either one. How many different ways? 1, 2, 3, 4, 5, and 6. Therefore, 3 times 2, 6. 6 possible outfits. Right? Let's see one more example quickly. Rosa's ice cream shop offers Rosa's ice cream shop offers 3 flavors and 4 container types. How many different flavor, container combinations are possible? Again, the Rosa's place 3 flavors. Let's say strawberry, mango, cherry, and chocolate. And 4 types of cones. 1, 2, 3, 4. How many different ways? 3 types of flavors and 4 types of containers. 1, 2, 3, 4. Each flavor. Right? The first choice is the flavor. There are 3 choices: strawberry, mango, and cherry. The second choice is the container. We have 4 choices. Therefore, we have 3 times 4, 12 possibilities. 12 possibilities. So, let's generalize this multiplication principle. The multiplication principle is not limited to 2 tasks. Suppose a process has several stages. Suppose A process has several stages. If task 1 can be completed in N1 ways, task 2 can be completed in N2 ways. And so on. Then the total number of complete outcomes is the total number of complete outcomes is N1 times, N2 times, up to Nm. There are m tasks. We multiply the number of choices available at each stage. We multiply the number of choices at each stage. Okay, that's the thing. Then let's go for the example. Three coin toss. A coin is tossed 3 times. A coin is tossed 3 times. How many possible sequences of heads and tails are there? How many possible sequences of heads and tails are there? Step 1. Identify the stages. Right? So, there are 3 tossers. There are 3 tossers. Right? So, each toss has 2 possible outcomes, head or tail. Each toss has 2 possible outcomes, head or tail. Therefore, we have the first toss, two possible outcomes. Second toss, 2 possible outcomes. Third toss, 2 possible outcomes. So there are 2 times 2 times 2, 8 possible sequences. 8 possible sequences. So let's list the outcomes. So we have first toss, head, head. Second toss, first toss, head, tail. With first toss head, we can earn head, tail, head, tail, head, tail, head, tail, head, tail. So the possible outcomes are head, 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 tail, head, tail, head, head, tail, 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 head, head, tail, head, tail, 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 head, tail, tail, tail. So the T diagram gives the same 8 outcomes here. At the first toss, the tree splits into 2 branches. Each branch split into 2 again for the second toss. Then each of those branches splits again for third toss. The T diagram explanation is very useful because it displays every stage visually. So each branch represents one choice. A complete path from the beginning to the end represents one complete outcome. The number of final branches equals the total number of possible outcomes. Right? Okay, let's move towards exercise. A restaurant offers 4 sandwiches and 3 drinks. How many meals are possible? How many meals are possible? The meals has 2 choices, 1 sandwich and 1 drink. Therefore, 4 times 3, 12. There are 12 possible meal combinations. There are 12 meal combinations. Let's go for the one more example. So, a license plate consists of 2 letters. A license plate consists of 2 letters followed by 3 digits. How many different license plates are possible? How many different license plates are possible? So in that case, for each letter position, there are 26 choices. For each digit position, there are 10 choices from 0 through 9, right? For each letter position, there are 26 choices, and for each digit position, there are 10 choices, right? From 0 through 9. Therefore, the number plate is with 2 letters followed by 3 digits, 26 first letter times 26 second letter, first digit, second digit and third digit. So 676,000 different license plates are possible. So, this answer assumes repetition is allowed. That means the same letter or digit can appear more than once. For example, uh, AA000 would be allowed. If repetition were not allowed, the number of choices would change after each selection. Right? Okay. Then, when should we multiply? When should we multiply? Use the multiplication principle when the word and connects stages of one complete process. Use the multiplication principle when the word and connects stages of one complete process. For an example, choose a shirt and pants. Choose an appetizer and soup and entry. Choose letter and a digit and another letter. Each complete outcome requires one choice from every stage. Right? So, then what are the common mistakes? Let's review the most common mistakes. Adding the number of choices instead of multiplying. So instead of multiplying the number of choices, the students can make that mistake, adding the numbers to get the number of choices. Forgetting one stage of the process. Assuming repetition is allowed when the problem says it is not. Assuming repetition is not allowed when no restriction is stated. Using the number of stages as the answer rather than multiplying the choices. Treating different orders as the same when order actually matters. Therefore, please keep those common mistakes in your mind, and let's summarize today's lecture. The multiplication principle is used when a process consists of several tasks performed in sequence. If the first task can be completed in m ways and the second task can be completed in n ways, then the entire process can be completed in m times n ways. For several stages, we multiply the number of choices available at every stage. We also learned how to verify outcomes using the T diagrams and how to apply the principle to routes, menus, coin tosses, license plates, passwords, and course schedules. The key question is how many choices are available at each stage. Once those numbers are identified, multiply them. Thank you for watching, and I will see you in the next lecture.